Before we solve problems involving Newton's laws of motion, let us discuss in more detail the nature of friction. We have learned earlier that frictional force is a kind of contact force, parallel between two bodies that resists, or opposes the motion of an object. It occurs because rough surfaces of two bodies tend to catch on one another, as they slide relative to each other. Even if the surfaces look smooth, at microscopic level, roughness can also be observed through tiny bumps. These tiny bumps get stuck on each other, that creates some mechanical bond, or glue, between the surfaces. The strength of friction between two surfaces depends entirely on the nature of the surfaces that are in contact, and the force pressing them together. This pressing force is usually related to the normal force. Of course, normal force develops because of the weight of the object. It increases the amount of contact that the object has with the surface at a microscopic level. With these, scientists describe frictional force between an object and a surface equal to a constant number called coefficient of friction, which is denoted by the Greek alphabet μ, multiplied by the normal force. Through experiments, scientists have measured the coefficient of friction for many combinations of materials. These coefficients depend on whether the objects are initially at rest, or initially moving, and on the types of materials involved. Table for these coefficients is provided in next section. Although friction resists motion, it helps us convert one form of motion into another. For example, just like we see in Newton's third law, friction allows us to walk on the ground. As we push backward along the ground, friction converts this into forward motion. Similarly, when car tires push backward along the ground, friction with the ground makes the tires roll forward. Friction also makes braking systems in motor vehicles and bicycles work. The braking system creates friction between the wheel and another object to slow down the motion. Since friction is created by the rubbing together of two bodies, it also generates a large amount of heat. Friction causes surfaces to heat up, results in wear and tear. In machinery, friction reduces efficiency as large amount of energy wasted as heat. Researchers were carried out to find ways to reduce friction, such as moving parts made as smooth as possible. Materials with very low coefficient of friction is used. Ball and roller bearings are placed between moving parts. This ball bearing enables the shaft to rotate smoothly. Surfaces separated by lubricant. Here, lubricating oil reduces contact between two meshing gears, and surfaces separated by air cushion. Just like in this figure, the air hockey table enables the puck to move smoothly when flicked by players. Now let us do a simple demonstration I made at home with my son Charles. This simple experiment will show you the effect of lubricant to the magnitude of friction. Here, we use baby oil as lubricant. As you can see, in this first figure, we have a toy operated by a spring and we let it slide on the whiteboard surface. In the second figure, we apply certain amount of oil over the surface of the whiteboard before sliding the toy. And on the third figure, we also put some oil on the wheels and internal parts of the toy. Can you tell the differences on the distance traveled by the toy? Can you describe the effect of oil to friction? There are two types of friction, static friction and kinetic friction. Static friction, denoted by F sub s, prevents a body from moving along the surface. It is the force that keeps a cabinet at rest even if we slightly push it and tries to move it along the ground. It is the same force that keeps a laptop from sliding off a table, even when the table is slightly tilted. So here by gravity, this laptop tends to move down the table. But the table exerts static friction, which is directed opposite to the tendency of motion of the laptop. Therefore, it will not slide. Of course there's a limit. If the table reaches its critical angle, then the laptop will begin to slide. We will take a look on this later. Static friction also allows you to carry a glass of water without slipping through your hand. Again, by gravity the glass tends to slide off your hand. But the upward friction exerted by your hand on the glass prevents this tendency of motion. Now, let us investigate in detail static friction. Again, consider box initially resting on the top of a table. Now, we draw the FBD of the box to see the possible forces acting on the box. In order to slide this box to the right over the horizontal table, we must first overcome the maximum static friction, denoted by Fs max, the surface exerts on the body. To do this we need to exert a force F parallel to the surface. The push exerted by the hand can provide this parallel force. This maximum static friction depends on the coefficient of static friction, denoted by mu sub s, between the body and the surface, and the normal force. Of course, normal force was developed because of the weight of the box. Therefore, Fs max is equal to coefficient of static friction multiplied by the normal force. Take note that magnitude of actual static friction may vary from 0 to the value of the maximum static friction. It can be 0, less than the maximum static friction, or equal to the maximum static friction depending on situation. And by Newton's third law, its value depends on the parallel force exerted on the body. To explain this, so here we have a box resting on the table. So the forces acting on the box are weight and normal force. Now consider a coefficient of static friction, μs, be 0.3, and the normal force exerted by the table on the box is 100 newtons. So using the formula maximum static friction, multiplying 0.3 and 100 newtons, will give a maximum static friction of 30 newtons. And this is the maximum friction that we need to overcome to slide the box. And this is the story. When we do not exert any force parallel to the surface, then definitely, the static friction is 0. In other words, if there is no action, there will be no reaction force. So the box remains at rest. When we apply a parallel force less than Fs max, say 20 newtons, by Newton's third law, the surface reacts to that applied force giving an actual static friction Fs of 20 newtons. At this point, the box still remains at rest since we still did not overcome the maximum static friction of 30 newtons. So if F parallel is less than Fs max, the actual static friction Fs is also less than the maximum static friction. In this case, this box is still at rest. Now if we increase the exerted parallel force equal to maximum static friction, which is 30 newtons. Therefore, the actual static friction will be also equal to 30 newtons. If this happens, the box is in the state of impending motion. Impending motion means that the motion of the box is close to happening, and about to overcome the maximum friction, but still the box is still considered motionless. So that's it. These are the possible values of static friction. Our baseline is that we need to know the value of the maximum of static friction, in order to predict whether the object slides over the surface when force parallel to the surface is exerted. Now let's examine any additional amount of parallel force, let's say it becomes 31 Newton, will finally overcome the maximum static friction and the box started to accelerate because of the imbalance force, or net force. When this happens and as the box slides over the surface, static friction is converted to sliding or kinetic friction, denoted by F sub k, whose value is always less than the maximum friction. Remember that kinetic friction acts when a body slides over a surface. It is a kind of friction when you are writing on a piece of paper using your favorite pencil, when the brakes slow down a wheel, or when a sliding book eventually stops. It is also important to note that a parallel force F must be present on the object to sustain its motion, either at constant speed or with acceleration. Similar with static friction, kinetic friction depends on the coefficient of kinetic friction, mu sub k, between the object and the surface and the normal force of the object. The table below shows the approximate values of coefficient of friction, both static and kinetic, for several pairs of objects. From these values, we see that for any pair of objects, the coefficient of static friction is usually greater than the coefficient of kinetic friction. This means that it is more difficult to start an object sliding than it does to keep it sliding. As you can see, the coefficient of friction of rubber on concrete is 1.0. This value is large enough to create traction between the rubber tires and the concrete road. Tire treads also helps to enhance contact with the tires, thus increasing traction. On the other hand, from this table, the smallest value of coefficient is the synovial joints in humans, that is around 0.003 to 0.01. This value depends on the condition of joint. Normal joints have very low coefficient of friction, while joint friction increases to those who are experiencing rheumatoid arthritis and osteoarthritis. So take care of your bones. Lastly, in some cases, the coefficient of friction can exceed 1.0. Solving problems using Newton's laws requires deep analysis and imagination. These abilities can be achieved by considering the following steps I'm going to present, a strategy in solving any problems in statics and dynamics. Number 1. Read and understand the problem. Before you solve any problem, make sure you clearly understand what problem is all about. Number 2. List down given information, as well as other important information not directly mentioned in the problem statement. Number 3. List down required or missing quantities. Number 4. Carefully draw free body diagrams or FBDs. Remember, this is the most crucial step. Be careful to check on the sign of the force, whether positive or negative, especially when the problem requires 2 or more interconnected FBDs. Number 5. You should know, on both x and y axes, the initial state of motion of the body, whether it is initially at rest or initially moving, and its final state, whether the body gains speed or slows down. This will help you to decide whether to use Newton's first law or second law. Number 6. Apply equations of Newton's first law, if the body is at rest or moving at constant velocity on a particular axis. If the body is either accelerating or decelerating on an axis, use Newton's second law instead. Number 7. If the problem involves friction, tell whether it is static or kinetic. Then apply the following equations. If the body is impending to motion, then use maximum static friction. If the body slides over a surface, use kinetic friction. Number 8. If the problem asks for kinematic quantities such as displacement, velocity and acceleration, you can use kinematic equations from Unit 1. Number 9. If the required quantity needs 2 equations, try to generate at least 2 different equations in terms of that required quantity. Then apply the method of solving simultaneous equations you learned from algebra. Try to follow these steps. And practice, practice, practice. These is all you need to do to successfully learn statics and dynamics. Now let us begin the real challenge. We will do a lot of problem solving. So please pay attention and listen carefully. Problem number 3. A 5 kg box is moving at constant velocity on a flat horizontal surface, by exerting a constant horizontal force F of magnitude 10 newtons. Letter A. What is the normal force exerted by the surface on the box? Letter B. Find the frictional force between surfaces. Now we try to imagine and draw the situation. Let's say this is the box. According to problem, it is moving on a flat horizontal surface. So we draw here a horizontal line. And it moves at constant velocity along this line. By applying a constant horizontal force F. And this is the force. After understanding the problem, we establish given information. Here we have mass m 5 kilograms. And the horizontal force 10 newtons. Then we list down required quantities. Letter A, the normal force. And letter B, frictional force. Here's the solution. First we draw the free body diagram of the box. We draw the x and y axis. And this is the box. Now we put the forces acting on the box. We have applied force F. The weight of the box, which is vertically downward. The normal force, perpendicular to the surface, and the kinetic friction, F sub k, since it is already sliding, and it is opposite to the direction of motion of the box. Now we're going to solve for normal force. To do this, referring to your constructed FBD, normal force is on the y-axis, so we will take the summation of forces along y. Then, think what law is to be used on y-axis. Since the box is only moving along x-axis, so at y-axis the box is at rest. Therefore, we will use Newton's first law. So summation of forces on y-axis must be 0. Now we combine the forces along y-axis. Just look on your FBD. There are only two forces on y-axis, the normal force and the weight. Therefore, the equation becomes, normal force N, minus weight W equals 0. We put here negative, because weight is downward. Remember, we need to take into account the proper sign of the force. Then, solving for normal force, we transpose weight W to the other side. Therefore, normal force N is equal to weight W. But weight is also mass multiplied by gravitational acceleration g. Normal force is 5 kilograms, times 9.8 meter per second squared. So the normal force on the box is 49 newtons. Now, for the kinetic friction. Again from FBD, friction is lying on the x-axis. Since the box is moving constant velocity along this axis, therefore we still use Newton's first law on x-axis. Therefore, summation of Fx equals 0. Forces along x-axis are the horizontal force F and the friction. So the equation becomes, applied force F minus friction. Solving for friction, F sub k, Fk equals negative of force F. So the kinetic friction is negative 10 newtons. Negative here indicates that the friction is towards negative x-axis. So that's it. This problem seems simple. As we go along, the problem will gradually become more complicated. And I want to emphasize something. Take note that normal force is not always equal to the magnitude of weight. We will see some situations later wherein normal force and weight are not equal. Let us continue to problem number 4. A 60-pound traffic light is supported by two wires as shown in the figure below. Letter A. Find the tension in the wires. Letter B. Assume that the wires are made from the same material. Which wire do you think will break first? Explain your answer. Now, listen carefully. Let us first understand the problem. There are three forces acting on the traffic light. Its own weight, and two tensions in wires, let's say, T1 and T2. As you see, this wire is measured 70 degrees from horizontal, while this one is 55 degrees from vertical. Again, before we solve, let us translate this into a free body diagram. We draw x and y axis. We put here the traffic light. Then we indicate the forces acting on the traffic light. The vertical weight of the traffic light, which is 60 pounds. We have tension 1, T sub 1, and this is measured 70 degrees above plus x-axis, since from this figure it is measured from horizontal. And this is tension, T2, is measured 55 degrees left of plus y-axis, because from the figure this wire is measured from vertical. Again, we are asked to solve for the tension in each wire, T1 and T2. Then, we are going to think which wire will break first. Now, since Newton's law of motion requires us to analyze forces along x and y axes, we need to transform these FBD in terms of the x and y components of the tension. For T1, we do some projections, so the x component of T1 is to the right, while its y component is upward. For the components of T2, again, doing some projections, so the x component of T2 is toward negative x-axis. And its y component is also upward. So let us further analyze. We can assume that the traffic light does not move. Therefore, we use Newton's first law for both x and y axes. We begin with x-axis. Summation of Fx equals 0. From FBD, we have two forces acting, the T1x and T2x. So we have T1x minus T2x. Don't forget to put here the minus sign since T2x is towards negative x-axis. Now we express T1x in terms of T1 and 70 degrees. So T1x is T1 cosine of 70 degrees. While T2x is T2 sine of 55 degrees. Then equals 0. Now we try to solve for T1 in terms of T2. We transpose this to the other side of the equation. So it becomes positive. Then dividing both sides by cosine 70. Simplify into 3 decimal places, so T1 is equal to 2.395 of T2. We do not know yet T2, so it is impossible, for now, to solve for T1. Just like what I have mentioned in problem-solving strategy, we need to generate one more equation to solve this problem. So we label this first as equation 1. We will return to this equation later. Now, we generate the second equation by taking the summation of forces along y-axis, which is by Newton's first law, equal to 0, since the traffic light does not move either in y-axis. From FBD, we have T1y, plus T2y, minus weight w, then equate this to 0. Then T1y is also T1 sine of 70 degrees, and T2y is T2 cosine of 55 degrees, minus 60 pounds, the weight, equals 0. Then we label this as our second equation. Now going back to equation 1, we will replace this T1 by 2.395 of T2 from equation 1. So this equation becomes 2.395 T2 of sine 70. Plus T2 cosine of 55, then we transpose 60 pound, so equals 60 pounds. Then can further simplify this since this equation is in terms of T2 only. So 2.395 sine of 70, plus cosine 55 is 2.824 of T2. Equals 60 pounds. Dividing both sides by 2.824. So T2 is 21.2 pounds. Then we go back again to equation 1 to solve for T1. So T1 is 2.395 times 21.2 pounds is 50.8 pounds. Is everything understood? So the tensions in the wires are 21.2 pounds and 50.8 pounds. Then for letter B. Since T1 is greater than T2, there is a Now let us do again exercises. Let us see what have you learned. Exercise number 2. Item number 1. In the figure shown below, a car engine with weight 2,200 newtons, hangs from a chain that is linked at the ring to two other chains, one fastened to the ceiling and the other to the wall. Find the tensions in these three chains, assuming that the weights of chains themselves are negligible. Hint: draw FBD of engine, and analyze to determine T1. Then, consider FBD of the ring to determine T2 and T3. Item number 2. A car weighing 1.96 times 10 to 4 newtons traveling in the positive x direction makes a fast stop. The x component of the net force acting on it is negative 1.50 times 10 to 4 newtons. Letter A. What is its acceleration? Letter B. If it stops after 2.00 seconds, what is its initial velocity? Item number 3. A certain force gives a 5 kg object an acceleration of 2 meters per second squared. What acceleration is produced on a 20 kg object using the same force? Congratulations for answering exercise number 2. Let us give another example. Problem number 5. A worker applies a constant horizontal force with magnitude 20 newtons to a box, with mass 40 kilograms resting on a flat horizontal frictionless surface. Letter A. What is the weight of the box? Letter B. Find the normal force exerted by the surface on the box. Letter C. What is the acceleration of the box? Letter D. What is the velocity of the box after 1.0 second? And letter E. How far from the starting point the box traveled after 1.0 second? So let us analyze first the problem by providing illustration. So this is the worker. And this is the box, initially resting on flat horizontal frictionless surface. So the initial velocity, v sub I, is 0. The worker applies horizontal force of 20 newtons. And therefore, the box of mass 40 kilograms, will definitely accelerate, especially the surface is frictionless. So 1 second later, it gains velocity, v sub f. We list the required quantities. Letter A, weight of the box. Letter B, the normal force. Letter C, the acceleration of the box. Letter D, the final velocity 1 second later. And letter E, the distance traveled. Now we translate the situation into free body diagram. Again, we draw x and y axis. Then we indicate the forces acting on the box. These are the force applied by the worker, the weight of the box, and the normal force. Now, let's begin the solution. Letter A. For the weight, so this is very simple. Weight W is mass times gravitational acceleration. So 40 times 9.8. The weight of the box is 392 N. Letter B. For normal force, we take summation of forces along y to be 0. So here we applied Newton's first law, since there is no motion happening on the box on y-axis. So the forces along y are normal force and negative weight. And this is equal to 0. Then we transpose weight to the other side. Normal force is equal to weight. So normal force is also 392 newtons. Again, in this problem, normal force is equal to the magnitude of weight. But I want to reiterate, this is not always the case. Please bear this in your mind. Letter C. To determine acceleration, we use Newton's second law for the x-axis. So the net force along x is mass m, multiplied by acceleration a. There is only one force acting on x-axis, that is the applied force by the worker. Hence this is also the net force acting on the box. Solving for a by dividing both sides by m. Therefore, acceleration is applied force by worker divided by the mass of the box. 20 newtons divided by 40 kg will give 0.5 meter per second squared. Now let us move on to letter D. For final velocity, we use one of the equation of uniformly accelerated motion. Vf equals Vi plus At. Substituting values, so Vi is 0, plus the acceleration from part C, 0.5 meter per second squared multiplied by time 1.0 second. So the final velocity is 0.5 meter per second. Finally, letter E. Solving for the distance. Assuming the box moves in straight line, so distance and displacement delta x are equal in magnitude. Again we use equation from m. Delta x is Vit plus 1/2 At squared. Substituting the values, so the distance traveled by the box 1 second later is 0.25 meter. So, there you go. As you can see, in this problem, we see how we integrate kinematic equations in dealing with Newton's laws of motion. We are, little by little, understanding the interrelationship of motion and force. In problem number 5, we analyze the motion of a box on a frictionless horizontal surface. Now in this problem, we will consider a surface with friction, both static and kinetic. Problem number 6. Letter A. What horizontal force F is needed just about to move a 3 kg box on a flat horizontal surface? Assume coefficients of kinetic and static friction of 0.4 and 0.6, respectively. Letter B. If the magnitude of the horizontal force F is 19 newtons, what happens to the box? If it accelerates, determine its acceleration. Try to think and analyze. So this is the box of mass 3 kg lying on horizontal surface, wherein the coefficient of static friction is 0.4 and for static friction, 0.6. The box is initially at rest. To make it just about to move, we need to apply force just enough to balance or overcome the maximum static friction. As we mentioned earlier, that at this point the box is impending to motion. And that is what we are going to find out. The force F needed, just to overcome the maximum static friction. We will also compute for the acceleration, just in case if the box accelerates upon applying 19 newtons of force. Now let us construct the free body diagram of the box. We draw again, x and y axes. The box lies on the x-axis. Then we indicate the forces acting on the box. The weight of the box. The normal force. The needed horizontal force to impend motion on the box. And the resistive maximum static friction. Then we are about to solve for the force F. Force F is on the x-axis, and we will consider Newton's first law for x-axis, since the box is impending to motion. So summation of forces along x-axis must be equal to 0. The forces along x-axis are the force F minus the maximum static friction, which is equal to 0. Again, don't forget the negative here, since the friction is pointing on the negative x direction. But the maximum static friction is also mu sub s times normal force n. Then transposing this to the other side. So the force F is also equal to mu sub s times normal force n. And that is also the maximum static friction. But we do not have normal force from the given information. So let this equation be your equation number 1. Let us solve normal force n by considering forces along y-axis. Since there is no motion along y-axis, therefore we also use Newton's first law. So summation of Fy is 0. Going back to FBD, the forces on y-axis are normal force n minus weight W equals 0. But weight is also mg. Then we transposed weight into other side. Therefore, normal force is also equal to mg. Substituting values, 3 kilograms multiplied by 9.8 meter per second squared. So the normal force is 29.4 newtons. Then we go back to equation 1. The force F is 0.6 times the normal force, 29.4 newtons. So the force needed just about to move the box is 17.64 newtons. This is the force need just to overcome static friction. In other words, this is the maximum horizontal force wherein the box does not move. A little greater than this amount will make the box accelerate. For letter B, if we apply a force of 19 newtons, definitely the box will begin to move or accelerates, since this value exceeded the maximum static friction of 17.64 newtons. Consequently, static friction is converted into kinetic friction since the box slides over the surface. The acceleration of the box can be computed using Newton's second law. So summation of Fx is equal to mass m, multiplied by acceleration a. So from this FBD, the forces on x-axis are the force, F and the negative of kinetic friction, F sub k, so this is equal to ma. But Fk is equal to mu k times normal force. So 0.4 times 29.4 newtons. The kinetic friction is only 11.76 newtons, which is less than the maximum static friction. So from this equation, we solve for acceleration a, by dividing both sides of the equation by mass m. So acceleration a is F minus Fk divided by m. Substituting the values. 19 newtons minus 11.76 newtons over 3 kilograms. So the acceleration of the box is 2.41 meter per second squared. Okay class. Do you have any question in mind? I hope this example gives you a clear understanding about friction and how it affects the state of motion of a body. In previous problem, we have seen problems in which the normal force on the body is numerically equal with its weight. In this problem, we will see a different case in which the normal force is less than the weight. Problem number 7. A 120-pound sled is pulled along a horizontal surface at a uniform speed, by means of a rope that makes an angle of 30 degrees above the horizontal. If the tension in the rope is 50 pounds, what is the value of the coefficient of friction? Now let us do this. Imagine this is the sled on a horizontal surface. Its weight is 120 pounds. It is pulled by means of a rope, 30 degrees above the horizontal. The tension in the rope is 50 pounds, that causes the sled to slide at constant speed. Now we are asked to solve for the coefficient of kinetic friction between the sled and the horizontal. To solve this problem, again we draw the sled's FBD. We draw x and y axes. Here's the sled. Then we indicate the forces acting on the sled. We have sled's weight, which is vertically downward. The perpendicular normal force N. The tension T, which is 30 degrees above x-axis. And the kinetic friction, Fk, which is opposite to the direction of the movement of the sled. Now we need to resolve tension in terms of x and y components. Since tension T is located on the first quadrant, so its x component, T sub x, is towards positive x-axis. And y component, Ty, is pointing the positive y-axis. Now, let us focus on the required quantity, and try to think of a formula from which the coefficient of kinetic friction appears. Do you think what is that formula? Go on, try to recall. Very good. We can use the formula of kinetic friction. Fk equals mu sub k times normal force N. From this equation, we solve for mu k. So mu k is equal to F sub k divided by the normal force, N. Since we do not have any of this, let us label this as equation 1. The next thing we need to do is to solve for Fk and normal force N. We can solve for kinetic friction, F sub k, using Newton's first law since the sled moves horizontally with constant velocity. So the summation of forces along x-axis is equal to 0. From our FBD, we see that the forces along x are Tx and negative Fk, then equating this to 0. Next, we express Tx in terms of the tension T and the angle 30 degrees. So Tx is T cosine of 30 degrees. Then we solve for Fk. Fk is equal to T cosine of 30 degrees. We substitute given information. Tension is 50 pounds multiplied by 30 degrees. Therefore, the kinetic friction is 43.3 pounds. We will substitute this later to equation 1. Next, it's time to solve for normal force N. We use again Newton's first law along y, since the sled does not move vertically. So summation of forces along y-axis is 0. Take a look carefully on your FBD. We will combine all the forces along y-axis. So the upward y component of tension, Ty, the normal force N, and the negative of weight. Then equate this to 0. We solve for normal force, by transposing Ty and W. So normal force N is W minus T sub Y. Substituting the values, 120 pounds minus 50 sine of 30 degrees. The normal force N is 95 pounds. This is what I told you before, that the normal force is not equal to the body's weight. You see that here, the normal force, which is 95 pounds, is less than its weight of 120 pounds. This is because the rope is providing an upward component, which helps the surfers to carry the sled. Is it clear, class? Now that we have already kinetic friction and normal force, we go back to equation 1 and substitute these values. So mu k is 43.3 pounds divided by 95 pounds. Therefore, the coefficient of kinetic friction between the sled and the ground is 0.46. Hello again everyone. This problem deals with free body diagram with a rotated axis, that we have not yet encountered before in our previous problems. And this problem is much different because we have very few given information. I guess we need more analytical thinking to solve this one. So listen very carefully. And do not sleep. Problem number 8. A block resting on an inclined plane. What should be the angle of inclination of the plane if the box is about to slide? Assume a coefficient of static friction of 0.6. Take note we have only one given information, the coefficient of static friction, 0.6. And we are asked to solve for the angle, to which the box is just about to slide down the plane. In other words, we are going to determine the maximum angle or critical angle, at which the box does not slide down the plane. Now, we construct first the free body diagram of box. Here we are going to use a tilted axis. That is, the x-axis is kept parallel to the inclined plane. So this x-axis is also tilted at an angle of equal to the angle of the inclined plane. And the y-axis is kept perpendicular to x-axis. Then we put here the box. Then we indicate the forces acting on the box. First, the weight W is always vertically downward. Be careful on this, weight is no longer parallel to y-axis since we use a tilted axis. Second, the normal force N, it is still kept perpendicular to the inclined plane. And third, we have the maximum static friction, which is towards up the plane or positive x-axis, since the box tends to slide down the plane. Now listen, for any problem which involves inclined plane, we will always resolve weight in terms of components relative to the tilted axis. So we do some parallel projections like this. These lines are parallel lines relative to x and y axes. We put here the angle, theta. Take note this theta is also the angle of the inclined plane. I want to reiterate, the angle between the weight and the y-axis is always equal to the angle of the inclined weight. Keep that in mind. And this is the x-component of the weight, pointing towards negative x-axis. While the y-component is pointing negative y-axis. Now that we have fully drawn the FBD of the box, I guess it's time to begin the solution. At first, we do not have idea where to begin. What formula should we use first? Don't worry too much. Remember, we have so much formula to begin with. Since the box does not move, we can use Newton's first law on both x and y axis. Now let us first use summation of forces along x-axis equals 0. From FBD, we have only two forces on x-axis, the Fs max minus W sub x. We put here negative since Wx is towards negative x-axis. Then equals 0. We transpose Wx to other side, so the equation becomes Fs max equals Wx. But we already knew that Fs max is also mu sub s times the normal force. And Wx is W sine of the angle, theta. Now look at this equation for a moment. Our goal is to solve for this angle. But the problem is that we do not know normal force and weight. It seems that we do not have enough information. We only have the coefficient of static friction, μs. So how do we solve this? And this is the time to use our critical thinking. We're going to do some elimination here. We need to eliminate all missing information such as normal force and weight. To do that, for the meantime, from this equation, we solve for normal force. Dividing both sides by μs, so normal force is W sine of theta divided by μs. And let us label this as our equation 1. After this, we're going to analyze the summation of forces along y-axis. Again we use Newton's first law, since there is no movement happening on the box along y-axis. Summation of Fy is equal to 0. Going back to your FBD, the forces on y-axis are normal force and negative of Wy. This is negative since Wy is towards negative y-axis. Then we transpose Wy to other side of the equation. So normal force is equal to positive of Wy. But Wy is also W cosine of the angle, theta. Then we label this as equation 2. And this is how the magic works. Are you ready? Since equations 1 and 2 are both normal force, we can equate these two equations. So W sine of theta over μs is equal to W cosine of theta. Surprisingly, we can cancel out W. Simplifying, by cross-multiplying cosine of theta and μs. Therefore, the equation becomes, sine theta over cosine theta is equal to μs. But from trigonometry, we have the identity that sine of an angle divided by its cosine is also tangent of that angle. Therefore, tangent of theta is equal to μs. Wow, we did it! As you see, normal force and weight are already eliminated. And we can now solve the angle theta since we have μs from the given information. We see also that this equation is independent on the weight of the box. Now, the moment we are waiting for. Let us solve the maximum angle, theta. So theta is equal to the inverse tangent of μs. The inverse tangent of 0.6 is 31 degrees. And this is the angle the inclined plane should have in order for the box to just about to slide. Or this is the critical angle at which the box does not slide. A little more than 31 degrees, the box. Alright, now it's your turn. Let us see again what have you learned. Exercise number 3. A toboggan loaded with students with a total weight of W, slides down a long snow-covered slope. The hill slopes at a constant angle of 35 degrees, and the toboggan is so well waxed that there is virtually no friction. What is the toboggan's acceleration? Hello everyone. Majority of the problems we have solved previously involve objects lying on surfaces. Now let us do some problem involving objects hanging on flexible materials such as cables, ropes and strings. Problem number 9. An elevator car is being driven by the attached cable. It allows the elevator car to move upward or downward. The combined mass of elevator and passengers is 1,000 kilograms. Compute for the tension in the elevator cable if: Letter A, the elevator is moving downward at constant velocity. Letter B, the elevator is moving upward at constant velocity. Letter C, the elevator is accelerating upward at a rate of 1.2 meter per second squared. Letter D, the elevator is accelerating downward at a rate of 2 meter per second squared. And letter E, the elevator is decelerating upward at a rate of 2.3 meter per second squared. So we have given information, the mass of the elevator and passengers, 1,000 kilograms. All we need to calculate is the tension in the cable at different situations. For letter A, we are going to solve for the tension in cable, if the elevator car is moving downward at constant velocity. So let us draw first the free body diagram of the elevator car. We use only vertical y-axis. The forces acting on elevator are, its weight W and the cable's tension T. And according to problem, for letter A, the elevator is moving downward at constant velocity. To solve for tension, We are going to analyze forces along Y. We use Newton's first law, since the elevator moves at constant velocity. Therefore, summation of Fy equals 0. The forces on y-axis are the tension T minus the weight W equals 0. But W is also mg. Then we transposed mg to the other side of the equation. So tension T is also equal to mg. Tension is 1000 times 9.8. So the tension in the cable is 9,800 newtons, when the elevator is moving downward at constant speed or velocity. Now let us solve for the tension if the elevator is moving upward at constant velocity. The free body diagram looks the same. The only difference is the direction of the elevator. We use again Newton's first law, since the elevator moves at constant velocity. Summation of Fy equals 0. Again, the forces on y-axis are the tension T minus the weight W equals 0. But W is mg. Then we transposed mg to the other side of the equation. So tension T is also equal to mg. Tension is 1000 times 9.8. So the tension in the cable is 9,800 newtons, when the elevator is moving upward at constant speed or velocity. As you can see, we arrived at the same answer regardless of different directions of constant velocity. Furthermore, we see that our answers in parts A and B show that if the elevator is moving at constant velocity, the tension in the elevator cable is equal to the magnitude of the combined weight of the elevator and passengers. For letter C, we will determine the tension of the cable when the elevator is accelerating upward at 1.2 meter per second squared. Since that there is already acceleration, therefore we will use Newton's second law. So the summation of Fy is equal to mass m, multiplied by acceleration a. But before we continue, we need to properly determine the proper sign of the acceleration, whether it is positive or negative. To do this correctly, we will use what we have learned in Unit 1. First we determine the initial direction of the elevator. Since the elevator is moving upward, its initial velocity is a positive value. Although we do not have a value for the initial velocity, it does not matter at all. Now in order to accelerate, the acceleration should have the same direction as the initial velocity. Therefore, acceleration is directed upward, hence its value is also positive. So the acceleration is positive 1.2 meter per second squared. Now, going back to this, the summation of forces along y-axis are tension T minus W equals ma. But, weight is mg. Then we transpose mg to other side, so it becomes T equals m plus mg. We can factor out mass m, so tension equals m times the quantity a plus g. Substituting values, so tension is 1000 multiplied by 1.2 plus 9.8. The tension is 11,000 newtons. Here we see that tension T becomes greater than the weight, 11,000 versus 9,800 newtons, when the elevator is accelerating upward. The cable seems to be stretched more than the usual. For letter D, we are asked to solve for the tension in the cable if the elevator is accelerating downward at 2 meter per second squared. Just like what we did in letter C, we need to determine the appropriate sign of this acceleration. So here the initial velocity v sub I is negative, since the elevator is moving downward, therefore acceleration a is also negative since the elevator is accelerating. The acceleration should be negative 2 meter per second squared. Then we apply Newton's second law. Basically, the solution is also the same as in part C. The only difference is the value of acceleration. So here we use negative 2 meter per second squared. Finally, the tension is equal to 7,800 newtons. Here we see that the tension of 7,800 newtons is less than the elevator's weight of 9,800 newtons, when the elevator is accelerating downward. The cable seems to get loose. As of this moment we see that the tension in the cable is changing, depending on what type of motion is happening on the elevator car. This varying tension is also the same when you are riding an elevator, then you feel a different sensation as the elevator moves. As the elevator accelerates upward, you feel heavier than when the elevator is initially at rest. But you feel lighter when as the elevator is decelerating upward. This variation in your weight is called apparent weight. And this is basically the effect of your inertia. For letter E, I leave that for you, to see if you really understand this problem. Please answer letter E, as your exercise number 4. Let us check what you have learned. Exercise number 4. Answer letter E of sample problem number 9. Good luck. Hello everyone. Are you feeling okay? I hope this lesson finds you at peace. The next 2 problems that we will encounter deals with pulley systems composed of 2 objects interconnected with flexible materials such as rope, cable, cord or string, that passed over a light frictionless pulley. Here are some examples of pulley systems. This one is composed of 2 masses labeled as A and B, connected by a cord and hang freely, such that vertical motion may occur, especially when the masses are not equal. We also assume here that the rope or strings does not stretch, so the tensions supporting each masses are the same. Another example is that one of the masses is lying on a horizontal surface, while the other is hanging vertically. They are connected such that when mass B accelerates downward, mass A will also accelerate to the right, considering that the tension in the string pulling the 2 masses are equal. In addition, we will use a different approach in constructing free body diagram. So please listen again carefully. Problem number 10. A light frictionless pulley carries a light cord to which is attached at one end a 7 kg and at the other end is 9 kg mass. Letter A. What is the acceleration of the system? Letter B. Determine the tension in the cord. Letter C. What is the acceleration of the system if the 2 masses are equal? Do your reasoning support the equation in part A? Letter D. If one of the masses is detached from the system, what will be the acceleration of the other mass? Do your reasoning support the equation in part A? Letter E. If there is no gravity, what is the acceleration of the system? Does your reasoning support the equation in part A? So let us establish the given information and analyze the problem. So here is the pulley, and this is the light cord. And at each end of the cord, we have unequal masses. Mass of A is 7 kg and mass of B is 9 kg. If we release both masses, of course, by means of gravity, mass B will accelerate downward since it is heavier than mass A. And since mass A is connected to mass B by means of this cord, mass A will accelerate upward. And that is what we are going to find out in letter A, the acceleration of the system. We will also determine tension in letter B. Letter C, we will determine the acceleration of the system as the 2 masses are equal. For letter D, the acceleration if mass A is detached from the system, that is, if mass of A becomes 0. And for letter E, the acceleration if there is no gravity. Now, let us draw the free body diagram of each mass. In pull systems like this, we will make some adjustment on the sign convention of the x and y axis. We will apply this simple rule: the direction of movement of the object will be treated as the positive x or y axis. So this is the y axis. As you can see, mass A is accelerating upward, therefore, following this rule, since the direction of mass A is upward, so we label this as positive y-axis and the opposite axis will be the negative y-axis. Then we indicate the force acting on mass A, so we have its weight W sub A, and the upward tension T. For free body diagram of B, so this is the y-axis and here is mass B. This mass is moving downward. So we label this as positive y-axis while this one is negative y-axis. Then you indicate the forces on mass B, so we have weight of B, and the tension T. So this is the adjustment that I am saying a while ago. In any pulley problems, you must take into consideration on the proper sign of our axis. You just follow this rule. you will always take the direction of movement of the object as the positive axis. If the object is moving upward, then take this as positive and the other side will be negative. And if the object is moving downward, so we will take this side as our positive axis. Now that we have drawn the free body diagrams, we first analyze mass A. We will use Newton's second law since mass A is accelerating. So summation of force along y-axis is equal to mass times acceleration. From FBD, the forces acting along y-axis are tension T minus weight of A, then equate this to mass A times acceleration. This is minus, since WA is towards negative y-axis. But weight mg, so WA becomes mass of A times g. Our goal is to solve for the acceleration. Since we do not know yet tension, we cannot solve immediately for A. So let us solve tension T by pretending that we know the value of acceleration A. Transposing this to other side, so tension T is mass of A times acceleration plus mag. Then we label this as your equation 1. Next, we analyzing mass B. We use again Newton's second law. So summation of force along y-axis is equal to mass times acceleration. From FBD, the forces acting along y-axis are negative tension T plus weight WB, then equate this to mass of B times acceleration. Notice that our tension becomes negative, since in our FBD, this tension is towards negative y-axis, and WB is positive since it is toward positive y-axis. I hope you see the difference between these two expressions. But weight is m times g, so W becomes mass of B times g. Again, let us solve tension T by pretending that we know the value of acceleration A. Transposing T to other side, it will become positive T, and transposing mass of B times A to the other sides makes it a negative, therefore tension T is mB times g minus mBA. Then we label this as your equation 2. Now that we have established two equations, the next step is to combine these two by equating them. So it will give the expression MA plus MAG equals MBG minus MBA. Then simplify further. Use your skills in algebra and solve for acceleration A. Finally, acceleration is gravitational acceleration g, multiplied by the difference of MB minus MA, all over the sum of mass of A plus mass of B. Then substituting the given information will give an acceleration of 1.23 meter per second squared. Wow, what a solution! Patience is a virtue. Remember this equation because we will use this to answer letter C, D and E. For letter B, now that we have solved the acceleration of the system, we can now easily solve the tension in the cord by using either equation 1, or equation 2. Let's say we use equation 1. From here, we factor out mass of A, so tension is mass of A, times the quantity, acceleration plus gravitational acceleration g. Substituting known values, so tension in the cord is 77.21 newtons. You can also use equation 2 to solve for tension. It should have the same answer. For letter C, we are asked to determine the acceleration of the system if the two masses are equal, that is, mass of A is equal to mass of B. Obviously, for a simple reasoning, if the two masses are equal, there is no unbalance force, therefore the system is at rest, hence the acceleration is zero. You can verify this from the general equation we have derived earlier from part A. Here, mass of A and mass of B are equal. If that's so, the numerator is 0. Therefore, the acceleration is 0. It's that great? That is the beauty of equation. It agrees with our common sense and simple reasoning. For letter D, again, simple reasoning works here. If we remove mass A, mass B is in free fall, therefore, its acceleration will be equal to gravitational acceleration 9.8 meter per second squared. We can verify this again using this equation. If we remove mass A from the system, then from this equation mass of A is 0. So we can eliminate mass of A, then the equation is reduced to g multiplied by mass of B divided by mass of B. We can cancel out mb. Therefore, A is equal to g. Lastly, for letter E, if there is no gravity, there is no weight or pulling force, obviously the system will not move even though the two masses are unequal, therefore the acceleration is 0. And from this equation, if g is 0, so as with acceleration. Now, it's time for you to shine. Show what you have learned by answering exercise number 5. Consider the system shown below. Assume coefficient of kinetic friction between block A, of mass 10 kilograms, and the table to be 0.4. Letter A, calculate the mass of block B, if this block is to descend at constant speed, once it has been set in motion. Letter B, what is the mass of block B, if this block is to descend with constant acceleration of 2 meters per second squared. Letter C, what is the mass of block B, if block